Dear students, today we are going to discuss whether we have a singular matrix or a non-singular matrix. Now, how to find out whether the matrix that you have is a singular matrix or a non-singular matrix. Now, of course, we know that for a square matrix, you can calculate determinant. Suppose you have a square matrix A such that if you compute the determinant of A and if it is equal to 0, in that case, we say that it is a singular matrix. Okay, that is how you identify whether a matrix is a singular matrix or a non-singular matrix. You have a square matrix and you compute the determinant of that matrix, and if it happens to be 0, in that case it is a singular matrix. Now for the square matrix, if you compute the determinant and if it is not equal to 0, then you say that it is a non-singular matrix. So that is how you identify whether a matrix is a singular matrix or a non-singular matrix. So for every square matrix you can compute a determinant. You just look at the value of the determinant, and if it is equal to 0, then it is a singular matrix. If it is not equal to 0, then it is a non-singular matrix. Now let us explain this with the help of an example. Let us write a square matrix. Now let's write A is equal to 1, 2, 1, 2, 4, 2, 1, 3, 2. Okay, this is a square matrix. This is a 3 by 3 square matrix because we have 3 rows and 3 columns. Now, when you look at this matrix, we can see that the first 2 rows are linearly dependent. Okay, when you just take a look at these two first and second row, these 2 rows are linearly dependent. And why do you say that these 2 rows are linearly dependent? Because the second row is just twice the first row, isn't it? 2 into first row, that will give you the second row. First row is 1 2 1, second row is 2 4 2. So you, when you multiply the first row with 2, you get the second row. So that is why you say that the second row is twice the first row, or in other words you can say that the first row is half the second row. So in that way you can say that these two rows, okay, first two rows are linearly dependent. Now, for a square matrix, if any two rows or any two columns are linearly dependent, when you compute the determinant, you will be getting a value that is equal to 0. Okay, remember, for a square matrix, if any two rows or any two columns are linearly dependent, just as you find in the case of this matrix A, where the second row is just twice the first row, or the first row is just half the second row. So these two rows are linearly dependent. So let us see what will we get when you compute the determinant of this matrix A. Determinant of A is, here we can write this as 1 into 4 into 2, that is 8, minus 2 into 3, 6, minus 2 into first row and second column. So you can write this as 4 minus 2 plus 1 into, this can be written as 6 minus 4. Okay, now this can be written as 1 into 2 minus 2 into 4 minus 2 is 2, plus 1 into 6 minus 4 is 2. So this can be written as 1 into 2 is 2, minus 2 into 2 is actually 4, plus 1 into 2 is 2. So this can be written as 2 plus 2, 4, 4 minus 4, 0. So this is actually a singular matrix because determinant of A is equal to 0. Now when you compute the determinant of a square matrix, and if you get a value that is not equal to 0, in that case we can say that it is a non-singular matrix. Okay, let us check with another example. Let us rewrite this matrix and let's see what the answer we get. Okay, let's write this as 3, 1, 1. Okay, now let's see how when you compute the determinant, what's the value you get. That is, the first row has been rewritten as 3, 1, 1. Okay, and the second row is given as previously 2, 4, 2. The third row is 1, 3, 2. Now let us compute the determinant. Now we can write this as 3 into 8 minus 6 minus 1 into 4 minus 2 plus 1 into 6 minus 4. Now this can be written as 3 into 8 minus 6 is 2, minus 1 into 4 minus 2 is 2, plus 1 into 6 minus 4 is 2. Now this can be written as 6 minus 2 plus 2. So this can be written as 6 minus 2 is 4, 4 plus 2 is 6. So this is not equal to 0. So from this we can say that since determinant of A is not equal to 0, this is a case of a non-singular matrix. Okay, so this is how you determine whether a matrix is a singular matrix or a non-singular matrix. You just compute the determinant, and if it is equal to 0, you will be able to see, you can see that it is a singular matrix, and if the value determinant is not equal to 0, it is a non-singular matrix, and you'll be getting a determinant value equal to 0 when there are any two rows or any two columns happen to be linearly dependent. Okay, only then you'll be getting a value that is determinant value that is equal to 0. I hope it's clear to you students. Okay, thank you.